Somewhere over Australia right now, a beam of light so faint it can barely be called light in any normal sense is leaving a rooftop, traveling hundreds of kilometers straight up and landing on a satellite. And the moment anyone tries to touch it, it knows. It changes. It tells on the person spying on it. That's not science fiction. That's a real device that got delivered to a real defense agency in July of this year, and it might be the reason your bank, your flights, and your power grid stay online the next time someone tries to fake a GPS signal over an entire city. Here's the thing almost nobody thinks about. GPS isn't really about maps. Sure, it tells your phone where you are, but the deeper job GPS does, the one that actually holds modern civilization together, is time. Every GPS satellite carries an atomic clock, and it constantly broadcasts a timestamp down to Earth. Banks use that timestamp to sync trades down to the millisecond. Power grids use it to keep electricity flowing in phase across thousands of miles of wire. Cell towers use it to hand your call off from one tower to the next without dropping it. Ships, planes, emergency dispatch systems. All of it is quietly synchronized by these signals falling out of the sky. GPS is actually just one system inside a bigger family called GNSS, Global Navigation Satellite Systems, which includes similar satellite networks run by other countries. But GPS is the one most of the world, including the US and Australia, leans on the hardest. And here's the part that should worry you a little. By the time those signals reach your rooftop, they are unbelievably weak. These satellites sit roughly 20,000 kilometers up, broadcasting with the power of a household light bulb, spread out across an entire hemisphere of Earth below them, which means they are shockingly easy to mess with. There are two ways to attack them. The first is jamming, basically shouting louder than the satellite so your receiver can't hear it anymore. Crude, but effective, and jamming devices are illegal in most countries, including Australia and the United States, yet they still show up through illicit channels because the technology to build one isn't especially advanced. The second attack is far scarier, spoofing. Instead of drowning out the real signal, spoofing fakes a better one. It transmits a false but convincing signal, one that looks completely legitimate to a receiver, and tricks the device into locking onto the wrong location or the wrong time. Your phone, your ship's navigation system, your bank's trading server, none of them have any built-in way to know they're being lied to. They just trust the signal, because for most of GPS's history, there was no reason not to. That trust is exactly what's being tested right now, in real time, in multiple parts of the world. GNSS interference has become a recognized ongoing issue rather than a rare event, with researchers and defense agencies describing it less like an occasional glitch and more like an active front in modern conflict. And here's what makes spoofing specifically dangerous compared to jamming. Jamming is loud, and devices can often detect that a signal has simply gone silent. Spoofing is quiet. It doesn't announce itself. It just quietly feeds a system the wrong answer, and the system keeps operating normally, confidently on false information. As software-defined radio and open-source tools become cheaper and easier to access, the technical barrier to attempting something like this keeps getting lower. And it's worth pausing on just how deep this dependency runs, because most people have never had a reason to think about it. Every card tap at a store gets a precise timestamp so it can be reconciled with the bank. Every airplane handoff between air traffic control zones depends on timing synchronization. Even your electricity staying at a steady 60 Hz depends on generators and substations agreeing on timing across huge distances. None of that was designed assuming someone might feed the system a convincing lie. It was designed assuming the sky could be trusted. Spoofing breaks that assumption quietly, without setting off any alarms, which is exactly what makes it more dangerous than a blunt instrument like jamming. So, what do you do about a signal that can be faked without anyone noticing? You stop trusting the signal by itself, and instead build something that screams the instant it's being tampered with. That's exactly what a team of Australian scientists just built. And the way they built it involves one of the strangest phenomena in all of physics. This is where CSIRO comes in. Australia's national science agency, the same kind of institution as America's NIST or NASA's research wing, just less famous outside its own country. In July 2026, CSIRO announced it had designed, built, and physically delivered 2 devices to Australia's Defence Science and Technology Group, based in Adelaide. CSIRO calls them quantum light sources. And what's inside that unassuming metal box is honestly one of the more elegant ideas to come out of quantum physics in years. Here's the analogy that makes this click. Imagine you and a friend each take 1/2 of a pair of magic dice, and no matter how far apart you travel, across a room, across a country, into orbit, the moment you roll your die and get a 6, you instantly know your friend's die also landed on 6, at the exact same instant, even though you never spoke to them. And their die is hundreds of miles away. That's roughly what quantum entanglement does, except instead of dice, it's photons, tiny particles of light. CSIRO's device takes a laser and, using what's essentially a specialized glass cube, splits it into pairs of photons that come out entangled, linked at a quantum level so that measuring one instantly tells you something about the state of the other, no matter the distance separating them. One of those two entangled photons stays on the ground inside an optical ground station. Its twin gets fired up into space to a satellite orbiting hundreds of kilometers overhead. And even after that journey, through atmosphere, through vacuum, across all that distance, the two photons stay correlated. That correlation is what makes this whole system spoof-proof, and here's why. Entangled states are incredibly fragile. If anyone tries to intercept that beam of light mid-flight, to read it, copy it, or fake it, the very act of touching it disturbs the quantum state. It's not like tapping a phone line where the intrusion can be invisible and undetectable for months. With entangled light, eavesdropping leaves a fingerprint that physics itself can't hide. There is no known way, under the laws of quantum mechanics as we currently understand them, to secretly copy or read an entangled photon without altering it. That's not a design choice CSIRO made. That's a rule of the universe they're borrowing. CSIRO calls this continuous process entanglement distribution. It means the ground station and the satellite can constantly check whether their shared timing link is still trustworthy. And the second it isn't, the system can switch to a different, uncompromised channel before any bad data gets used downstream. Think of it like a security guard who doesn't just check IDs once at the door, but keeps rechecking every single second someone is inside the building, and instantly locks every door the moment something looks off. This general idea, using entangled or individual quantum particles to detect eavesdropping, isn't brand new to physics. It's part of a broader area called quantum key distribution, developed for years mostly for secure communication over fiber optic cables on the ground. What makes CSIRO's work notable is the specific application, pointing that concept at the much harder problem of ground to satellite timing, where the signal has to survive atmospheric turbulence, the curvature of the Earth, and the sheer distance of low orbit, all while staying portable enough to deploy in the field rather than confined to a fixed laboratory setup. CSIRO's technical lead in the project, Dr. Matt Broom, described the delivery of these devices as a significant milestone in the development of quantum secure time transfer, which sounds like a modest sentence, but sit with what it actually means. This isn't a lab demo running on optical benches bolted to a table that never moves. This is hardware that had to be shrunk down, ruggedized, and made portable enough to sit at a real ground station and actually fire photons at a real satellite hundreds of kilometers away. Reliably, outside of laboratory conditions, exposed to temperature swings, vibration, and everything else the outside world throws at delicate optics. That's a genuinely difficult engineering problem, and it didn't happen overnight. The project actually traces back to a research collaboration with Heriot-Watt University in Scotland, whose scientists had worked out much of the underlying source design in laboratory settings. CSIRO's job was to take that theoretical groundwork and turn it into something field deployable, something that could survive being carried out to an optical ground station instead of living permanently in a climate-controlled physics lab. That's the unglamorous part of innovation that rarely makes headlines, turning an elegant idea on a whiteboard into a box that actually works when you take it outside and point it at the sky. Now, here's where I have to be honest with you, because a lot of coverage of breakthroughs like this skips the uncomfortable part. This is not a finished deployed system protecting your bank account tonight. As of the official announcement, CSIRO has not published a timeline for full operational deployment, and there is no confirmed date for when this moves from delivered to a defense research group to actively running across a national timing network. The devices were built primarily for the Australian Defence Force, specifically to keep military systems synchronized, even in GPS-denied or GPS-degraded environments. Think electronic warfare zones, where an adversary is actively trying to jam or spoof navigation systems. CSIRO has said the same underlying technology could extend to civilian infrastructure, power grids, banking, transport, emergency services, but could extend to and is currently protecting are two very different sentences. And right now, the technology is only at the first one. There's also the question of scale. 2 devices delivered to one facility in Adelaide is a proof that the engineering works. It is not, by itself, a national network. Getting from here to something that actually shields an entire country's timing infrastructure would require many more ground stations, satellite cooperation, and years of testing that haven't happened yet. And Australia isn't operating in a vacuum here, which is honestly the more interesting part of the story once you zoom out. Other countries have been racing at this same problem from completely different angles. The United Kingdom has already flight tested a quantum navigation system called QINS, developed with UK research and innovation funding, which uses ultra-cold atoms instead of entangled photons, a fundamentally different piece of physics aimed at a similar goal of navigating without relying on a satellite signal that can be spoofed. In the United States, the Department of Transportation has put roughly $12 million into a mix of programs, including reviving an older ground-based backup system called ELORAN and exploring low Earth orbit satellite backups for GPS. Here's the honest caveat, though. No independent head-to-head comparison of these different approaches, quantum entanglement, cold atom navigation, ELORAN, LEO backups, has been published yet. Nobody can currently tell you with confidence which of these will actually win out as the dominant solution. And if a video tells you otherwise, be skeptical of it. What CSIRO's entangled photon approach does appear to be, based on current reporting, is the first system of its specific kind delivered to an actual defense customer in a portable, field-ready form. That's a real distinction. First doesn't always mean best, but it does mean CSIRO has jumped ahead in one particular race, even while the overall race for GPS resilience is still wide open. So why should anyone outside Australia, especially in the United States, actually care about this? Because GPS spoofing isn't a hypothetical problem confined to conflict zones on the other side of the planet. It's a recognized national security concern in the US and UK as well, precisely because so much critical infrastructure quietly assumes GPS timing will always be honest. If a hostile actor ever managed to spoof timing signals across a major financial exchange or across a segment of a national power grid, the disruption wouldn't look like a movie hacking scene. It would look like transactions failing to reconcile or a grid losing synchronization it didn't even know it depended on. That's the kind of failure that's invisible until the moment it isn't. And it's exactly the kind of failure this technology is designed to catch before it can cause damage. There's also a quieter second layer to this story. CSIRO has framed this project as part of building Australia's sovereign quantum capability. The country wants the know-how to design and manufacture this kind of hardware domestically instead of depending on other nations for it. Quantum technology, broadly, is shaping up to be one of the defining technical fields of this decade, the way semiconductors were decades ago. Countries that can only buy this kind of hardware from someone else are in a fundamentally different position than countries that can build it themselves. Australia, investing in that domestic capability now, is a bet on where the value of quantum technology will sit 10 or 20 years from now. It's also worth thinking about what this means for the relationship between defense research and everyday technology, because that pattern shows up again and again in history. GPS itself started as a military project before it ever ended up guiding your car to a coffee shop. The internet's earliest backbone was built for military and academic research before it became the thing you're using to watch this video. There's a fairly consistent pattern where technology developed first for defense, under pressure and with serious funding, eventually filters down into civilian life once the engineering has been proven out and the cost comes down. CSIRO's quantum light source is currently sitting at the very beginning of that same pattern, funded and driven by a defense need, tested in a defense context, with civilian applications described as a future possibility rather than a current reality. Whether it actually follows that same path from military tool to everyday infrastructure is something only time, funding decisions, and further testing will answer. Nobody, including CSIRO, is claiming otherwise right now. There's something almost poetic about the physics underneath all of this, too. For decades, quantum entanglement was the thing physicists argued about in thought experiments. Einstein famously called it spooky action at a distance, because it unsettled him so much, a phenomenon he wasn't fully comfortable accepting, even though the mathematics demanded it. It lived in textbooks and philosophy debates about the nature of reality, tested in careful laboratory experiments over decades to prove it was actually real and not some flaw in the equations. Now it's sitting in a metal box on an Australian rooftop, quietly protecting the timing signal that keeps your flight on schedule. That's the kind of transition that doesn't happen very often in science, an idea moving from "we can barely believe this is true" to "we're now engineering around it" in the span of about a century. If you found this as fascinating as I did, this channel covers stories like this one, real breakthroughs explained honestly without the hype. So consider subscribing for more. Let's bring this all the way back to ground level for a second, because it's easy to lose the thread in the physics. This story is not really about photons, or glass cubes, or satellites hundreds of kilometers overhead. It's about trust, specifically the quiet, invisible trust that modern life places in a handful of signals falling from the sky. Signals most of us never think about until the day they fail. CSIRO's answer to that trust problem isn't a bigger lock or a stronger password. It's a system that uses the fundamental rules of quantum physics to make lying about the signal at a physical level essentially self-defeating. You can't fake an entangled photon without the fakery showing up in the physics itself. That's a genuinely different category of security than anything built purely out of software or encryption keys, and it's worth understanding on its own terms, rather than folding it into hype about the quantum revolution in general. What CSIRO has actually proven here isn't that quantum technology has solved GPS security overnight. It's proven something quieter and, in a way, more important, that the physics behind quantum entanglement can survive the jump from a laboratory optical bench to a functioning piece of field hardware, firing photons at a satellite hundreds of kilometers away, and still hold together well enough to detect tampering in real time. That's the actual milestone. Not a finished shield around global infrastructure, but proof that the shield is buildable, that the hardest part, making the physics work outside a lab, is no longer the obstacle it used to be. What happens next? Whether this scales into the systems protecting your bank, your flights, your power grid, depends on funding, testing, and years of quiet engineering most people will never hear about. But the foundation just got laid, quietly, on a rooftop in Adelaide, using a piece of physics that used to be too strange for even Einstein to fully trust. And if you want to understand where the next decade of infrastructure security is actually heading, this is one of the places worth watching. If this kind of story is worth your time, hit like so more people see it. I'll see you in the next one.